Okay, we're recording. So we will be doing a digit recognition system, and to do this, we will be using the convolution neural networks. And reason for using convolution neural networks is other than your normal neural networks, it is a more specialized version for image classification. And for using neural networks is other than your regular classification algorithm like logistic regression. This way you can identify a lot of sensitive data, and you can do the classification much faster and easier. So these are the libraries that we'll be using. So we'll be initializing the numpy embed seed. So by initializing this, we it pretty much can makes the random numbers that we produce predictable, and the rest of the libraries. Okay, so rest of the libraries are imported. Now we will be importing the test set dataset and the training dataset. Two datasets for this given problem are given. The training dataset has 42,000 images and the test dataset has 20,000 images, and they are arranged in they represent 28 by 28 images of handwritten numbers, but they are represented in one-dimensional vector of 784 784 dimensional vector, and for each pixel a corresponding column will be there, and another column will be there named label. This will include the number that is represented in the image. So for every pixel there's a column, and the number representing all these 784 columns is represented in the label. So we will include them now. Okay, wait, why? Oh. Well, I'll pause this. Okay, so the training data and test data are uploaded. So now we have to separate the dependent variables and independent variables from the training data set. So as I mentioned, the label has the number which the image corresponds to, so it is the independent variable. So it is y, and we will do that, and next will be the rest of the 784 columns will be extra. So we'll execute that. Now we will delete train because it is not needed. Okay, and now we'll check whether the numbers are distributed properly. That is what I've been trying to do here. So let's execute that and see what happens. As you can see, these are the numbers. So there are one there are 484, and for the least one is 5. There are 3,795 fives. And if you can, this graph, it's distributed pretty evenly, not perfect, but can be used. So now we'll check if there's none values, and okay, so there are no null values, which means we can go to the next part, and the next one we will be normalizing the data. So we will normalize data because uh, the data is distributed between 1 to 255, so then it's easier for the convolution layer to converge the numbers between 0 and 1. So this is why we will be using grayscale normalization. Okay, now as I mentioned earlier, the images are in a one-dimensional vector, and for convolution layer to apply its filter maps and apply filters and get filter maps to identify for the identification of certain features, the image had to be on a 3D dimension. To do that, so we will be converting it to its original shape, which is a 20 by 28 by 28 matrix. And since this is a grayscale image, we will be using only one channel. If it's a RGB one, then there will be 3 for R and G, and for B, and this is a for only one is needed when it's only grayscale. So we will execute that. Okay, so you can see it's done. Now we will one-hot encode the values on the Y train. As you know, the values are from between 0 to 9, and the algorithm might recognize 9 as a higher value than 0, which is not true because it is a categorical variable. So we will one-hot encode this. Okay, now it's done. Now next thing, we will be splitting our data set. The training set, we have a separate test set, but we will be needing a cross-validation set. To do that, we will set the random seed first. You don't have to set it, you can straight away input this one, but I will set it. And then you can execute this train test split function to split this, and the test site is 0.1 of our this is test site, but this is the cross validation site, and our 10% of our training set will be using for cross validation, and the random seed we have already initialized. By initializing this, the values that will be taken to validation will be randomly selected. So you can see the train x val, it is the x values of the validation set, then y train and y val, it is y vals of the validation set, and now we will execute it, and they will be appear in this variable section. So now we will be doing modeling of our CNN, the neural network. First we have to do is do the convolution layer, then we will be doing max pooling, after that dropout, then again the next two conversion layers, then again max pooling, then dropout, then flatten, then the fully connected layer, then the final output layer. That's the structure. So before that, because this is a sequential convolution neural network, we have to run this one. Okay, it's done. So this is the first two layers. You can see that in the input shape is the inputs that we will be given, the shape of the inputs, so the shape of the images that we will be given to the first convolution layer, and it will be 28 by 28 image, and the one is there because it's a grayscale. If as mentioned, if it's RGB, then it will be 3, and the activation function is relu, we can use sigmoid or binary or whatever the activation that you can use, but for this the standard one is relu. And the kernel size, this is the dimensions of our what do you go feature feature sorry feature matrix, I think. Yes, so there will be 32 feature matrix and their dimensions will be 5 by 5. So basically it's a 5 by 5 matrix of and a 0 and 1 will be corresponding to each one. So these matrices will be they are based on, so it basically the convolution layer will convert our image into 32 different images, and to do this they will be using a 5 by 5 matrix, and the values of these matrices will change depending upon the 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 images. So if an image, if there's a particular characteristic in a certain image, that characteristic will be represented in the feature map, and the feature map, which is the filter, and the filter will be matched against our 28 by 28 image, and it will check whether if this feature is present in that image. So after that, again the same process is done. As you can see, there is no input shape because input shape is of course now different, and since it comes after another convolution layer, the KRS will identify the shape of this incoming image, and it will do the same process. It will have 32 filters, and the filter size will be 5 by 5 matrix, and it will identify features, important features in these 5 by 5 matrices. And by using max pooling, we basically downsize the image. It will still retain the original important features that were identified in the filters in the above two layers, but it will be condensed. So what it will do is it will be take 2 by 2 matrix, and it will for every 2 by 2 matrix of the incoming convolution image, convolved image, the maximum number present in each image will be taken. So the maximum number represents the important features that are present in the image. So important features will be preserved while downsampling the size. Dropout is a regularization. So basically 25% of our neural network will be ignored for each epoch. By doing this, we will get a more distributed way of knowing, recognizing, classifying the image. So same process is done here. Instead of 32 filters, in the next layers there will be 2 convolution layers so far. In these convolution, instead of 32 filters, we will be using 64 filters, and the matrix size is 5 by 5, but here it will be 3 by 3. Activation function is of course relu, and again max pooling is done here, and again dropout is done. By flattening, for computational purposes, 28 by 28 matrix is not viable, so we will again make it a 784 dimensional vector, but of course it won't be 784. It is in our original image, but this is a downsized image. So basically it will convert this whatever matrix that is coming through these layers, and it will convert into one dimensional vector. Then we have our fully connected layer. This is the hidden layer in our neural network. So it is fully connected, and that is why we have dense here, densely connected, and we will have 756 nodes in our fully connected layer, which is our hidden layer again, and activation function is relu. And after that we will have our final output layer, and for output layer we will have 10 nodes, and each node will represent the number from 0 to 9. and the activation function is softmax, because once you put softmax, the probability should always be 0. So by putting softmax, the probabilities that is calculated per each image will always the sum of these probabilities will always be equal to 1. Basically, if probability of getting 0 is 90%, the probability getting the rest of the digits is 10%. So once we do that, then the convolution layer neural network is set up. It is done. So I will execute this. Okay. Now next we will have the optimizer. The optimizer will be that we will be using is RMS prop. The optimizer will be used to optimize our gradient descent, and another optimizer that we can use in this specific problem is the stochastic gradient descent, but we will be using RMS prop because it's quicker and the values are the default values. So we will be executing this, then we will be compiling the model. So optimizer we have already set up above, and the loss function, loss is categorical cross entropy. If this is a binary classification, yes or no, 0 1 classification, then it will be binary cross entropy, and the metrics is accuracy. The thing that we'll be checking is the accuracy. So then we'll be using the learning rate reduction. So basically, if we have high learning rate throughout the gradient descent process, then it might end up making us settling in a local endpoint. So to prevent that, we will be using learning rate reduction and reduce RL on plateau function will be used, and we will checking the value accuracy for 3 epochs. So basically, for 3 epochs our learning rates will not be changed, but if there's no progress, then our learning rate will be halved by 0.5, and the minimum learning rate that we can get is this. So we will execute that. When we fitting the model, we'll be using this we'll be using this as a callback. So basically, when we are training, we will be reducing our learning rate. Okay, now we will be using the now we will be declaring the number of epochs. So we will use only 1 epoch for this example. To get more high accuracy, we can use more epochs, and the batch size will be 86. So batch size. So okay. Now the next one is data augmentation. So basically, by data augmentation, we will essentially be increasing the number of features that we have in our data set. So by having more features, the accuracy will be increased. So by data augmentation, at least 2-3 times our features will be increased. What it does, it basically changes our data, changes our images into different section based on some values. For example, this feature wise center, it set input mean to 0 over data set. It is not clear, but if you look at this horizontal flip, it randomly flips images, it vertically flips the images, height will be shifted, width will be shifted, images will be zoomed, images will be rotated. By doing this, we can get different features from the same image. So By doing this we can get more features and it increases our accuracy. So to do this, you can get, there are image augmentation in the case documentation. You can get these values, and you can just simply copy paste it here and modify it according to your need, and I run it, and this will be again fitted, and when we fit our dataset this will be included. Okay, now we will fit datagen.flow. This is because our training dataset is not in the image form, it is in CSV file. So datagen.flow is the method that we will be using, and of course xtrain, ytrain will be used. Batch size we already defined as 86. Epochs we already defined as 1. Validation data, we separated these data in the previous section. As you can remember, 10% of our training set is divided for this one, x val, y val, verbose 2. Steps for ECOP is basically the number of columns into the batch size. So batch size is, you can think this as mini batch gradient descent. So for all of our columns, for all of our features, the theta values, so the theta value should be modified for steps, and there are 784 steps for one image, and there are 86 images in one batch. So 784 into batch size should be our steps per epoch, and it will be represented in this one. We already defined this, and after that callback, we mentioned this one, it will be callback. So our learning rate will be changed based on whether we will be making progress with our current learning rate. So we will fit this one. This will, for one epoch it will take around 5-6 minutes, so I will stop it. So basically this will produce 86% accuracy, and if we use, instead of one epoch, if we use 30 epochs, like for an example, this will be training for 3 hours or so, but will produce more than 95 to 99% accuracy. And this is the whole system. So that's it. That's the register recognition system that is implemented using convolutional neural networks. Thank you.